Having been in this session all day with all the atmospheric science talks, I can tell you that my talk kind of is spanning a few scales. So it's not quite at the micrometer scale, it's also not quite at the climate scale, but sort of a broad range in between. And I specialize in radiative transfer, especially in cloudy atmospheres, so that's what I'm going to be talking about today. First, I want to acknowledge Blue Waters with the boilerplate statement there in the middle, and let you know that this work would not have been possible without that allocation, and especially without the graduate fellowship I received, both from the Blue Waters program as well as from the NASA Earth and Space Science Fellowship program. And I just finished up my PhD in January at the University of Illinois, and I've since moved on to a postdoc at the Cooperative Institute for Climate Science, which is between Princeton University and NOAA's Geophysical Fluid Dynamics Lab. Okay, so first I want to give you some background information about the importance of radiation to weather and climate. So radiation is the main driver of all the circulations going on in the atmosphere, whether from global scale, just the incoming angle of solar radiation causes the tropics to heat up more than the poles, so it sets up this large-scale circulation on average, or even at fine scales like sea and lake breezes, where the different heat capacities of land versus water induce a circulation. And that's how you get the nice cool breeze when you're by the shore. So clearly, radiation is important to represent well in all of our climate and weather models in order to get these circulations of many scales right. And those models are often evaluated with satellite remote sensing data sets because they cover a global picture of observations. And all the observations we get from space are actually inferred from direct measurements of radiation. So what you don't see is there's a middle layer, which is a model inversion of that radiation to all the atmospheric variables we're interested in, like surface temperature, cloud and aerosol properties. But it's not just the horizontal distributions, or the horizontal gradients in temperature that matter. It's also the vertical distributions. And clouds are a major factor in the vertical gradients of heating and cooling in the atmosphere. I put this figure here just to kind of summarize that a lot of the radiation emitted by the atmosphere and the surface, the thermal radiation, is absorbed by clouds before the rest of it can escape to space. And on the other side, the solar radiation coming in, about a third of it is immediately reflected back to space by the atmosphere and clouds. And so you can see that clouds are important, and this figure is showing you that they're pretty much everywhere. This is the cloud fraction, the annual average cloud fraction as observed by the MISR satellite instrument for the year 2007, and with red being close to 100% cloudy on average. So to allude to a question asked earlier about the tropics already are a pretty cloudy place, so increasing moisture there might not necessarily reflect back more solar radiation. And also, it's hard to make, those tend to be really juicy, bright clouds. It's hard to make bright clouds brighter just by adding more water. So how is radiation currently represented in our models? We've seen that it's important, so how good are we doing? Well, I put this equation up here, which is the 3D radiative transfer equation, and this is just for a monochromatic point. So you'd then have to do an integration over the whole spectrum of relevant electromagnetic radiation. But this is not how it's represented in our models. It's too complicated of an equation to solve. So I just put this here to show you that we know the physics, but also to remind you that it's not that we don't know it, which is why we don't represent it well. It's just that it's too expensive. So this is a picture of clouds, 3D clouds, illuminated by the sun from a slightly off overhead angle. That's how they might look from space. And this is a cartoon representation of a similar thing, just to show you that you get areas of shadows and bright spots when you allow radiation to move in 3 dimensions. But because we have to simplify it in models, this is how it's actually represented. So we're only going to solve the 1D radiative transfer equation, which means that properties can only vary vertically, not horizontally. So we've got horizontally homogeneous clouds that extend infinitely, essentially, in the horizontal. This is what a plane parallel cloud looks like. Thanks for the laugh. Okay. I didn't get any laughs with that joke last year. So in reality, we often make a compromise, which is called the independent column approximation. And so what that approximation is doing is essentially breaking up the domain into multiple columns and treating each of those columns with the plane parallel approximation. So what ends up happening is the radiation incident in a column, whether it's from the sun or whether it's being emitted by the atmosphere or the surface, is constrained to stay within that column. So you can see when it looks like it should leave here, it actually just comes back in the other side. It's like having periodic boundary conditions in each column for your radiation. So that's okay. We're still representing, some horizontal variability. It's better than the plane parallel approximation across the whole domain. But you can also see that we end up with the displacement of the shadows in the bright areas compared to a full 3D representation. So displacement in these shadows and bright areas means displacements in our heating and cooling of the atmosphere as well. And that's going to mean alterations to our circulations. So you can see, you can find in the literature, if you dig through, some anecdotal evidence that our 1D approximations aren't good enough, both from a remote sensing perspective and from cloud modeling perspective. For remote sensing, pretty much it results in these unacceptable errors in important data sets that we use to evaluate key climate variables. So if you're evaluating your climate models with what you assume to be the truth and it's actually biased by these 1D approximations, you might end up kind of tuning to the wrong answer. From a modeling perspective, restricting, kind of as I mentioned before, restricting the horizontal radiative transfer is going to impact your cloud scale circulations and therefore your modeled cloud properties, especially as you increase spatial resolution. So what's needed here is to go back and reevaluate our 1D approximations, since we have the computational power to do so. And that means developing a highly accurate 3D and broadband benchmarks and models to quantify the bias and not just rely on anecdotal evidence anymore, to inform the future parameterizations and satellite inversions. So this is just a sampling of the publicly available models that are out there. And in this quadrant, in this big blank space, which is the intersection of broadband, which means integrating over the electromagnetic spectrum, and 3D, allowing radiation to move in all dimensions, there's a hole, and that's where I came in with blue waters. So before we can answer any interesting science questions or quantify the bias, this model has to be developed. So to address the broadband component, what I did was use another Monte Carlo method to sample the spectral space and assign radiation to a particular frequency. And to capture the 3D radiative transfer, I used also a Monte Carlo method, which samples paths of photons, or really not literal photons, but kind of radiative energy packets and what path they might choose through the atmosphere. And that involves at least 10 to the 9 of those samplings per simulation. And each of those have many interaction points, which require many comparisons between random numbers and probability distribution functions. So you can see how all the calculations are adding up. And that's why blue waters was needed to address this problem. And of course, to get results then for all those computations in a timely fashion, we needed massive parallelization, which we could also achieve on blue waters. So these are kind of more specific objectives, as I already sort of alluded to. What I was going for with development was a 3D radiative transfer model, both that could solve monochromatic and broadband simulations. I wanted it to be publicly available for use in development eventually because it wasn't there for me. And I wanted to give back to the community, and I think that also results in a better vetted model and less time spent reinventing the wheel, which means less time that we have to move it forward. It was also important to document the accuracy at a very high level so that it could truly be a standard of comparison for other models. I should have mentioned on a previous slide, there are 3D broadband models out there, but they're proprietary. They're kept within closed research groups. So this community model could be used as a standard of comparison for those, given the high accuracy that it's being done at. Flexibility in application means that it can apply to remote sensing problems, to cloud modeling problems, over user-defined ranges of resolution and both spectral and spatial, and also to make good use of HPC resources. That was important to me as well. Okay, so I'll walk you through a little bit of how the model is designed. What I did was start with a monochromatic 3D community model. And I kind of built on top of its figure from its paper here. So that model solved a forward radiative transfer equation, only considered a solar source of radiation. So I went ahead and added thermal emission, which means the radiation coming from the surface and clouds in the atmosphere at longer wavelengths. But then to make it broadband, I had to figure out a way to integrate over the electromagnetic spectrum. And that's when I came across in engineering literature a Monte Carlo technique to doing that. So basically, you're using a Monte Carlo method to sample the spectral space and assign a frequency to each of those energy packets. And then what we get out is radiance, flux divergence, outgoing fluxes. These are all things that you could use for a variety of atmospheric radiative transfer problems you're trying to solve. So incorporating it with realistic atmospheric properties meant building these databases of gas properties and cloud properties at very high resolution, and also gathering a PDF of the solar source function. So those are all the new inputs that had to be added. And what's not represented on here is kind of the large loop of how the work is done in this model. Essentially, each of these statistical samples, which I'll call photons, are grouped into units of work called batches. And the user gets to define the number of batches and the batch size at the beginning of the simulation. And each batch is the unit of work assigned to a rank by the master process. And when it finishes that batch, it goes back and asks for more. And that continues over and over until all the batches have been assigned. And then a collective MPI call is used to get the results back from all the ranks and produce the output file that contains the user-specified output quantities. So there were some community products that were unanticipated when I initially proposed this project. As I've already discussed the monochromatic and the broadband models, I knew those were going to be outputs. But what I didn't anticipate was building these property databases and the fact that they could be useful not just for this application, but for other people. So the intention is to make these databases and the workflows to subset them also available as community products. And I'm going to go into a little bit more detail about them in the next few slides. And then additionally, to provide benchmark results for other modelers to compare to, modelers who don't have access to resources like Blue Waters where they can't run the model on their own, but they can at least evaluate their own model with the output from mine. Okay, so we can, I'll start by talking about the gaseous absorption database. So this figure is just kind of showing you the high variability in gas absorption in the atmosphere. It happens at a really high frequency. So you need very high spectral resolution to resolve it. I think I mentioned on the previous slide it was something like 250 megahertz resolution. So I used realistic atmospheric properties. The maximum file size ended up being about 3.5 gigabytes for this table. And that's incorporating about 6 million spectral points. And it's just one number that you need to save for each of those spectral points. So for a variety of realistic atmospheric properties, I utilized some existing databases out there, including HYTRAN 2012, which gave me the line strengths. Those then had to be broadened, so I used this tool called ARTS to do that, and it incorporated some of the continuum absorption, for those of you familiar with atmospheric radiative transfer lingo. And so it was important to me to take advantage of the tools that were out there to do this non-trivial work. And I compared to the textbook values of absorption cross-section, and it looked really great. And as I just mentioned a bit ago, the database, not just the database, but the tools and the workflow used to create them and to subset them are going to be available as part of this project. So I similarly also had to make a database of liquid water droplets using me theory. And that table was quite a bit bigger, about 1,000 times bigger, because I had to save a lot more values to describe not just the absorption, but also the scattering. So some of the scattering profiles included up to 1,000 members, and there were, let's see, 60 different values of effective radius and about 4 to 5 million spectral points. So you can see how that multiplies quickly. I also evaluated these with values found in the literature, which you can see here. This is a plot from a paper in the Journal of Climate. And if you compare the thick black lines here to the thin black lines below, which are from my model, there's good agreement. And one of the things I hope to do, or that I hope somebody else does once the tables are released, is utilize the high resolution database to update the parameterizations that we use for cloud radiative transfer. Those are shown here in the step functions. And these parameterizations were developed at least 20 years ago and are still ubiquitous in our weather and climate models. So maybe they could stand to be updated, and I think this database would be a great way to do that, utilizing it, data mining. So on to some of the benchmark cases. I started with one-dimensional cases just because there were already comparisons published in the literature between 1D models and the 1D standard of comparison, which is a line-by-line model. So I compared my model in 1D mode to that line-by-line model, and this is showing you a profile of heating rate for that case. It was pretty good. It's a little bit off down here in the low levels, and that just has to do with vertical resolution issue. And as I increased the vertical resolution of my model, the results converged to this red line. So that's nothing to be worried about. And in the table here, I'm showing fluxes at the top and bottom of the atmosphere for a variety of cases. And going through each of these isn't important. It's just here to show you that we got within 2% or less for each of these cases. So this was my first attempt at benchmarking in a 3D cloud case. So we started with a very simple cubic cloud, and this has like a long heritage in the radiative transfer literature. It's the first 3D test case. So that's why we chose it. It's very simple to represent. And so what I'm showing you here are cross sections of the cloud heating rate, or cooling rate if it's blue. And this is for identical clouds other than the plane parallel approximation was used here, and here we have a fully 3D cubic cloud. So let's say that, oops, I want to go this way. Let's say we have a photon emitted from inside the cloud at this point on both figures, and it's traveling in this direction. What happens when it gets to the edge there for the plane parallel cloud is, since I mentioned in my introduction, it treats it like it has periodic boundary conditions, so it just comes back in the other side. And what this means is you can never get cloud side cooling from the plane parallel approximation or an independent column approximation. Whereas with the cubic cloud, the photon's allowed to escape out the side, which then contributes to the cloud side cooling here at the edge of the cubic cloud. So let's just remove those arrows to make it a little easier to see. You might notice that at the top and bottom of the cubic cloud, the heating rate is identical, or effectively identical, to the plane parallel cloud, right in the center there. But here at the cloud edges, you have very strong cooling, and that is completely unrepresented in the plane parallel cloud. So since the plane parallel approximation, or some version of it, is used in all of our climate and weather forecasting models, all of those models are missing out on this cooling. So it's not going to be allowed to feed back on the cloud circulations, on the temperature distribution, and then on the cloud circulations. And although I haven't yet coupled it to a dynamically evolving simulation of a cloud, that's sort of the hope in the future work, to really see what impact it has on cloud properties and cloud dynamics. So some of the computational challenges I faced in this project, first being the input data table size. I know it's nothing compared to the data sets that some of you guys are working with, but It is a little bit rough to try to move that table of me properties, that 3.8 terabyte table. So one of the workarounds I used was just to subsample it to the range of spectral resolution and effective radius that I needed for that particular simulation. And of course, utilizing Globus for movement. If anyone out there is not using Globus yet, you should start, because it just makes data movement so much faster. There were some memory issues. The biggest factors in the memory footprint of the model are, of course, the grid size and the number of spectral points. And I also discovered towards the end of my PhD that there was a memory leak in my model, which Galen kind of helped me diagnose a little bit. So essentially, the memory footprint is increasing on the node with each batch that the node computes. So that definitely will have to be addressed if I want to go to more complex. It's right now limiting the complexity of the simulation I can do. And then finally, balancing the batch size and the number of ranks that you use for efficiency. If I have too few batches per rank, it results in a load imbalance because some of them are doing way more work while others have finished, an hour ago. Too many small batches per rank results in an MPI bottleneck because they're all trying to go back to the master to get another batch to work on at the same time. So it's important, I'd like to define before releasing these models publicly, some good ranges for people to stay in as a rule of thumb, but it'll be important for any user to kind of test it out on a small scale before doing a big job. So the future directions I'd like to move in with this project, if I can, would be to simulate more complex cloud cases as benchmarks. I want to get clouds that look a little bit more realistic, but that's going to require resolution of the memory leak. I have some leads on it, so whenever I find time after I'm done writing my papers, I will get back to that and fix that up. Then I definitely would like to characterize the performance and scaling on blue waters. That was something I hoped to do before the end of my PhD, but I just ran out of time on that. I have looked a little bit at performance, but I haven't done a detailed scaling analysis. And then finally, I really would like to couple to a dynamic atmospheric model to really look at the relative importance of this cloud-side cooling compared to other factors like entrainment that Sonia was talking about and the evaporation that happens at cloud edges. So I think I'll probably, instead of throwing it right into some huge domain, I'll probably start at a very small scale, a single cloud, maybe even a parcel model, that kind of thing, and then go to a large eddy simulation where maybe you've got a 10-kilometer domain, but at least you have a field of clouds to see how they interact with one another. But doing that is going to require development of on-the-fly interpolation scheme for those gas and cloud property databases within the model, because it's no longer going to be a single time step where there's fixed properties. The properties are going to start evolving, and you can't know what they're going to be a priori. So that will have to be done as well. Okay, so let me summarize some of the original benefits of this work. This is going to be the first publicly available broadband 3D radiative transfer model, and along with the tools, databases, benchmarks, it's going to be the first benchmark class 3D broadband model for intercomparisons and evaluation of other models, and hopefully provide accuracy bounds for the development of parameterizations for larger scale models. I've also provided the largest known database of me properties. Those are the cloud property table I developed, which can be mined for other uses. I haven't shown everything here for time's sake, but I've well documented the accuracy of this model with each of the benchmarks that I've tested it with for both analytical and real atmosphere test cases. And I think this is the first application of the Monte Carlo spectral integration technique in atmospheric sciences, which is an unbiased way of doing the broadband integration. The model is also very flexible in its application. The user gets to define the range, resolution, and the optical properties used. The modular source code is going to be available for development.